Hello, Frank. I put together a presentation to walk you through the system that I'm quoting for your property. This system will be a grid-tied battery backup system for your home. This slide covers the agenda for today. So first we'll start off with the site evaluation, then we'll move into the component review for each of the main components that I want your system to have. Then we'll move into the system diagram as well as cost breakdown and wrap up with a discussion of operations and maintenance. Just as a recap of the information that we reviewed during our last meeting, this system will be located at your Raleigh, North Carolina single-family home. You're interested in a grid-tied battery backup system with a capacity for 3 days of energy storage. The loads that you want to be able to operate normally during a 3-day power outage are highlighted in the table on the right. The main item to highlight is that we have a budget to keep, so we chose to not build a storage system large enough to operate your major power loads like the AC, washer, dryer, and dishwasher. After removing those energy items, the total daily energy consumption for the green rows is 8,734 watt hours per day, with a maximum potential power consumption of 3,365 watts. Now we'll dive into the specific components for your system. The inverter that has been specified for your system is the Outback Radian. The specification for this inverter can be seen on the table to the right. The inverter was initially investigated because it is a hybrid inverter, and the system we are designing is a grid-tied battery backup. The maximum power consumption of the green rows in the previous slide is 3,365 watts. So the Outback Radian has plenty of capacity to handle nominal loads as is specified for 4,000 watts. This inverter will also respond well to any dramatic surge loads as it's rated for 8,500 watts for a 100 millisecond surge. Measuring in at 28 inches by 16 inches by 9 inches, this unit is compact enough to have flexibility for installation location. The system we are designing needs to be autonomous for 3 days. The highlighted rows in the load table on slide 3 equal 8,734 watt hours for daily energy consumption. Using this value, we calculated that we needed 682 amp hours to meet your storage needs. Using these calculations, I specified 4 Concord Sun Extender AGM batteries. The total amp hours for the specified system exceeds the minimum requirements, so that will help with the longevity of the product by lowering the depth of discharge during use. The size of these batteries is 20 inches by 10 inches by 10 inches, so the 4 batteries are small enough to be stored indoors in a temperature-controlled area of the house, removing any additional wear or performance reductions due to weather. An evaluation of the charge time leads us to believe that these are correctly sized batteries for our system, as it's estimated it'll take 4.6 hours of full sun to complete a full charge. This was calculated using the formulas provided by the battery supply manual, also shown on the slide above. The power requirements that we calculated for the solar array were 2,638 watts and led us to specify a 2x5 array of Canadian Solar monobifacial solar panels. The 10-panel array provides us with an estimated 2,800 watt system when the panels are operating under NMOT conditions per the specification table, which can be seen on the slide above. NMOT performance was chosen over STC to provide a more accurate portrayal the performance we can expect to see on a daily basis. Wiring 2 panels in series provides us with a 48 volt output to match the other system components. The cost per watt for the solar panels is favorable when comparing to competitors. This keeps the panel count to a minimal 10 panels, making this an easy system to secure to your roof. Sizing the charge controller was completed with the STC conditions, as that would provide us with the worst case scenario. Short circuit current for the panels at STC is 9.93 amps, and with 5 parallel strings, the maximum current rating for the controller should be based off of about 50 amps for the array. After derating calculations, we specified the Outback Power Systems FlexMax 80 MPPT charge controller. This model is very flexible and can work at multiple voltages, but it will operate at 48 volts just like the rest of our system components. This model is also efficient with a 97.5% conversion efficiency. This slide shows a basic breakdown of the proposed system. The 10-panel solar array will be mounted to your south-facing roof. The power generated by the array goes to your charge controller that is stored indoors in a utility closet. Also in that utility closet are the 4 storage batteries. When the batteries are full, the power from your solar array passes through the charge controller to the inverter and is either distributed to the house or back to the grid. The inverter will be stored in your garage. This is a practical, affordable, easy to maintain system, and that is why I believe it is a great investment for you and your family. A big part in component specification was their cost. This table breaks down the cost of the main components discussed in today's presentation. This is not the total cost of the project. Our labor team is creating an estimate for the labor as well as commodity components like wiring and hardware, and we plan to have you a full quote within the week. One item I wanted to highlight was the battery costs. We spoke a lot of the current industry-leading lithium-ion technologies, but after looking at your budget, it did not make sense to double the battery cost with a lithium-ion equivalent to the AGM batteries that we specified. Now I'd like to change directions with our discussion and move on to the operations and maintenance portion of the system. Each system I design takes into account a robust O&M plan, and I highly believe that following the plan gives you the best performing product. Every O&M plan will have KPIs that you need to keep track of for your system, and I've assigned 4 to your system: the Power Performance Index, the Energy Performance Index, Battery Charge Rate, and Battery Discharge Rate. Now the PPI and EPI are pretty simple calculations. PPI is measured power over expected power, and the EPI is the measured energy over the expected energy. This can all be calculated from your data logging controller. So that's a good transition to all your information is being logged in the Outback PowerMate 3S system display controller that was purchased with your inverter. This is a key product in maintaining your system, as it'll log all the performance data that you need over the life of the system. A proper O&M plan will help you get the best performance out of your system and in turn increase the system's longevity, return on investment, and total availability. This slide covers some of the most common types of maintenance for a proper O&M plan. In the administrative maintenance category, we request that you store any component literature that you receive. And you also need to verify that logging functions are enabled for the inverter controller. For preventive maintenance, top items I'd like to discuss today are we'll have annual battery enclosure cleanings, annual corrosion inspections, annual wire inspections, and module torque inspections every 5 years. So there's a mix of annual maintenance as well as multi-year maintenance. The most common corrective maintenance for systems like yours is battery replacement, as battery durability has not caught up to the other components. And finally, we do have some condition-based maintenance, the array cleaning depending on the system output, which you can see on your inverter controller. The bottom portion of this slide also outlines the qualifications that we require for our O&M team. These qualifications come from the NREL handbook and guarantee a great product in your operations and maintenance plan. And that brings us to the end of the presentation. Thank you so much for your time, and I hope you choose us moving forward for solar system installation at your residential home in Raleigh, North Carolina.